So next up is designs, moving on to waves and oscillations. So we have a pendulum question here. It says grandfather clock that is running slow, and which of the following adjustments will fix it? To do this, it's running slow, so that means that the period of oscillation is too long. So the equation that you have in your equation sheet is that the period of a pendulum is 2 pi square root of L over G. So if the period is too long, that means that this number here, T, is too big, which means that this number here, L, is too big. So we would like to we'd like to make L smaller to make T smaller. So if you want to make L smaller, you need to raise the weight. So the answer there is A. Next, we have a sinusoidal wave on a string. What's the speed of the wave? And we should also check that we are comfortable getting wavelength, period, and frequency. So this is a graph of displacement of the wave as a function of space, and here's a snapshot graph. So if displacement of the wave is a function of time. This is going to be an easy way to figure out time information, so that'd be the period and the frequency. And this one here with the x on the x-axis is going to be a better way to figure out wavelength. So the wavelength is the period of one complete cycle, so that's going to be start here and in here, and that's 0.6 meters. And the period here is going to be the time to complete one complete cycle, so the period is going to be 0.2 seconds. The frequency is 1 over the period, so that is 1 over 0.2, which is 5 inverse seconds, which is also known as 5 hertz. When we're done, what's the speed of the wave? Well, the speed of the wave is going to be the wavelength times the frequency. So that's going to be 0.6 meters times 5 hertz, which is 3 meters per second. I probably disagree with this problem that you could actually answer that question to 2 sig figs, but it's multiple choice, so it's definitely closer to 3 than it is to any of the other ones. Next up, we have a spring question, and certainly a multiple choice. This would be long for a multiple choice question, but a multiple choice question could have any one of these little parts to it. So let's do the spring question. So we have the spring stretches 5.4 centimeters when there's a fish hanging from it. What's K? What's the spring stiffness constant? And then what will be its amplitude and frequency if the fish is pulled down and released so that it oscillates up and down. So in the first case, we have that we can use this first bit of information to figure out the spring constant for this spring. So it stretches, maybe rather than calling that delta x, I'll call it delta y, because I'm assuming that the fish is hanging, is going to be 5.4 centimeters, so I'll write that in metric. And the mass is 2.4 kilograms. So if we use the fact that the spring force is K delta y here, there's a negative in this equation. That negative just indicates that the force points in the direction toward the equilibrium position of the spring. But for the most part, you can just, like many of the equations with negatives in it this semester, kind of use your brain to figure out the sign or the direction of the force. That negative there is just sort of there as a clue to you. So the spring constant, which is what we're solving for, is going to be the force over how much it stretches. The force is just the weight of gravity, so that'll be mg over delta y. So we have 2.4 kilograms 9.8 meters per second squared, 0.054 meters. And I got 436 newtons per meter, which I'll round to 440 at 266. Okay, next is B. So now we're setting that spring into motion, and we pull it down 2.1 centimeter and then release it. So I've told you the amplitude here. Don't make it harder than it needs to be, because you certainly can. I've pulled it down 2.1 centimeters and released it, so the amplitude of that new oscillation is 2.1 centimeters. You could write that as 0.021 meters if you wanted. Either way would be fine. So now we need to figure out the frequency of this. The equation for the frequency of a spring is an equation on the equation sheet. And it's this: 1 over 2 pi square root k over m. We have all of those numbers, so we can just plug it in. 1 over 2 pi square root of 436 newtons per meter divided by 2.4 kilograms, and you get 2.1 hertz.